In 3.7, we will be talking about inverse functions. We will talk about how the domain and range will act. We'll hopefully find the inverse from a graph and also from an actual function. So when we think about the way that a function works, a function takes an input, puts it in, it does something to that input, and it comes out. What an inverse does, it reverses the process. So a y goes in, becomes an x. Now the notation of an inverse is you just put a little -1 next to whatever they have named the function. So you can, if you see here, our function is an f, you can write that as f to that little -1. You read that as f inverses. Now, only one-to-one functions have an inverse, and two functions are inverses if, when you compose them, you get x both ways. So f of g of x will get you an answer of x. G of f of x will get you an answer of x. Now, the reason that happens is if I stick x into a function, it becomes a y, and then if I stick that into an inverse, it becomes an x again. Or I can go do the opposite way. If I stick y into an inverse, it becomes an x. If I stick that x into a function, it becomes a y again. So it reverses the process. So the thing to remember about domain and range, the domain in f will be the range of our inverse. The range of f will be the domain of our inverse. So our function goes from a to b, our inverse goes from b to a. So if we look at our example, it says in a particular function that is one-to-one, f of 2 equals 4 and f of 5 equals 12. What are the corresponding input and output values for the inverse? Well, this is telling us that our function has the 0.24 in it and the 0.512. So our inverse has to have the 0.42 in it and 12.5. So our inverse of 4 is 2. Our inverse of 12 is 5. You'll see how they have turned those around perfectly. So if a 0.24 is in the function, then the inverse will have to have the 0.42. And so then 512 is in our function, so the 0.125 is in our inverse. Now we can test whether or not two things are functions. If we compose them, f of g would have to equal x, and also g of f would have to equal x. So when they ask us to test whether things are inverses algebraically, that's exactly what we're going to do. Now we know how to do f of g and g of f. So what we're going to do is we're going to take the f function, we're going to put g inside of it, we're going to take the g function, we're going to put f inside of that. Now that's going to test if you recall how to deal with functions. So watch that particular notation. So in our first one, we are going to input f, or into f, I'm sorry, we are going to input the g function. It's going to go right there. So we're going to get 1 over x minus 2 plus 2. The positive 2 and the negative 2 cancel, so we get 1 over x, which is just x. So our first direction worked. If I composed and put g into f, I got x. Now let's go the opposite way. This time into our g function, we're going to put 1 over x, so it's going to go right here. 1 over x plus 2. So we're going to get 1 over x plus 2 minus 2. Well, 1 over anything is its reciprocal, so if we flip over 1 over x plus 2, it becomes x plus 2 over 1, which is just x plus 2. So the plus 2 and the minus 2 cancel, and we just get x. So we can say, yes, they are inverses. So again, if I put g into f and f into g, and both times, once simplified, I get an answer of x, then yes, they are inverses. Let's look at another one. So we are going to test x cubed as our f function, and g of x is 1/3 x, and are those inverses? So first let's try f of g of x. So let's take our f function and plug in 1/3 x. So what does our f function do? Our f function takes our input and it cubes it. So we're going to take our input and we're going to cube it. Now when we cube it, we cube both the fraction and the x, so we get 1 over 27x cubed. We did not get an answer of x, so we can immediately go, they are not inverses. Now if it checks one way, you automatically should check it the other way, just in case. But in this case, as soon as you get one that doesn't get you an answer of x, you stop. You say they're not inverses. Now let's talk about our parent functions and which ones have inverses and which ones don't. Now these are all functions, but we have to test for inverses whether or not they pass the horizontal line test. So a horizontal line does not pass the horizontal line test, so there is no inverse. Our identity function is its own inverse. So this is the function y equals x. Its inverse is y equals x. That's very unusual for that to happen once in a while. The quadratic function does not have an inverse. Sometimes what we'll do is we'll only use half of it. So we will say that our domain is just from 0 to infinity. And by using just 0 to infinity, we will only use this half of it, so that we do have an inverse, so it would pass the horizontal line test. So if you use the positive half alone or the negative half alone, you can force it to have an inverse. The inverse is the square root function. So this is your y equals x squared. And as long as you kind of cut it in half, you can use the fact that it does have an inverse. This passes your horizontal line test. It is a cubic. This is y equals x cubed. This is y equals the cubed root of x. These ones are inverses. Our second one here, that is our rational function, 1 over x. It is its own inverse. It does pass the horizontal line test. Horizontal lines only hit it one time. It's its own inverse. It's kind of weird like that. This does not pass the horizontal line test unless you use possibly one little swoop instead. So there's no inverse here. Square root has an inverse of y equals x squared is the inverse of the square root of x as long as we only use half of it. And the absolute value has no inverse because it fails the horizontal line test. Now, I'm not going to ask you those per se, but I just wanted to show you how they worked in the parent functions, and then you'll kind of get an idea of how they're going to work in the transformed, changed functions. So here we have a function. They say to find g of 3 and g inverse of 3. So first, let's talk about g of 3. In this particular one, that means that x is 3, and they want to know what is the y. So we just go over to the graph, and the answer is 1. At an x value of 3, we have a height of 1. So that means that the point 3, 1 is on our g function. But if we do the inverse, so if we're doing the inverse at 3, that means something different. This means at a y of 3, what is our x? So if we have the original function, where does it have a y value of 3? And that's why we only need 1 to pick from. So our original function has the point 5, 3. So our inverse will have the point 3, 5. And so the answer would be 5. So you have to switch it around. Now, if we have some functions and we actually want to find the inverse, we are going to switch the x and y, or whatever variables are used. You're going to solve for that new y. We're going to rewrite the function in function notation. We may have to restrict the domain if needed. We can use the original range to tell us what the new domain is going to be. So let's look at some functions and let's find the inverse. So this is a formula that allows us to solve for the Celsius if we know the Fahrenheit degrees. And now let's think about the rules that we talked about on the last slide. We're going to switch the x and the y. We're going to solve for wherever the new y is sitting. So our new y is sitting right there. So we need to solve for that y. So the first thing I would do is I would get rid of 5/9 and make it 9/5. To divide by 5/9 to get rid of it, we can multiply each side by the reciprocal. And the only thing left is for us to add 32. So now we know that our inverse is going to be 9/5 x plus 32. So in our original function, our f was our input, so our Fahrenheit was our input. In our new function, our Celsius will be the input, and we will get out a Fahrenheit. So let's do the same thing for the next example. So I'm going to make it y notation. I'm going to flip-flop the x's and the y's. And I want to solve for this y here. Now that y is in a fraction. So what we're going to do is we're going to get that fraction by itself. Let's subtract 4 from both sides. Now, what I would do if one side is a fraction, one side is not a fraction, put it over 1, and then let's cross multiply. So we would get x minus 4 times y minus 3 equals 2. Now, if you distribute in the x minus 4, it's not going to help a whole heck of a lot. So just divide that quantity off and add 3 to both sides. Now, the original function notation was f of x, so where this is sitting right here, the last step is to put in the function notation. So f inverse is 2 over x minus 4 plus 3. Let's take a look at this one. So let's make it y notation. Let's flip-flop the x and the y. And then we've got to get this by itself. So let's subtract 2 from both sides. Now what's going to get rid of a square? What's going to get rid of a square root is a square. So let's square both sides. So we get y minus 4 equals x minus 2 squared. Now you could, if you wanted to, actually physically square that, x minus 2 times x minus 2, but you can leave it, and we can just then move this 4 to the other side. Now we move that 4 to the other side by adding 4 to the other side. So we get x minus 2 squared plus 4 equals y. And now remember, put that in inverse notation. So we get the quantity of x minus 2 squared plus 4. Now technically, we could say that the domain of our inverse, since it normally doesn't have an inverse because of a square on it, would be the range of this. So if we know what that graph looks like, we could tell you what x is to use and what x is not to. Now let's talk about what the graph of an inverse looks like. So the first thing I would do is I would take on my original function. There's 2 points here that are really good. This is the point, I'm going to list it on the side. That is the point 2, 1, and the other one is the point 1, 0. And then I'm going to guesstimate where 2 more points are. So that looks like it's about the point 3, 1.5. Let's get one over here. That one doesn't look too bad. It looks like it's about, let's go 0.2 and down 2. So if I know what those points are doing, my inverse switches them around. So the inverse will flow through the points 1, 2, 0, 1, 1.53, negative 2, 0.2. Now, one thing you can also do to guide you when graphing the inverse is the two functions will always be reflected over the line, our identity line, y equals x. Okay? So let's go ahead and put those points on, and then we can think about if I flipped it across that dashed line. So at 1, 2 is a point on our inverse, 0, 1, 1.53, and negative 2.2. And our inverse function looks something like that. And if you could picture this being rotated across that line, you would get the graph that you see there. So that's a little bit about inverses, and your homework is right down here.